Welcome to this explainer on plant machinery installation. Today, we're focusing squarely on one of the most critical, yet honestly most frequently misunderstood phases of setting up rotating equipment. We're talking about section 3.10, the final alignment. Now, if you've ever worked on a massive industrial site, you know that just getting a heavy pump and a motor physically set on a foundation feels like a massive victory all on its own. But we're going to uncover why perfectly aligning a machine just once is literally never enough. We'll explore the invisible physical forces that wreck our hard work and the microscopic tolerances required to finally truly hand a piece of equipment over to the owner. Okay, let's dive into this incredibly frustrating scenario. Imagine this. You or your highly skilled millwrights have just painstakingly completed the first alignment. You've dialed in the pump shaft and the motor shaft. They are perfectly parallel, perfectly centered. The foundation is set, you feel amazing about it, but suddenly, further down the project timeline, you're told you have to perform a final alignment completely from scratch. It feels totally redundant, doesn't it? I mean, why redo a job that was already finished to perfection? Well, the harsh reality of the plant industry is that a machine doesn't exist in a vacuum. Between that initial first alignment and the final handover, the construction happening all around it continues. And those subsequent construction steps introduce severe, often unnoticeable external forces that completely ruin all your prior hard work. To the naked eye, the machine looks exactly the same. But at a microscopic level, its geometry has been violently warped. A brilliant example of this is the piping connection process. Before the plant can move forward with hydrostatic testing, which is where they pressurize the lines to check for leaks, and line flushing to clean them out, the piping team has to connect massive steel pipes to the pump's suction and discharge flanges. For beginners, flanges are just the flat rims where the pipes bolt together. The suction is where the fluid enters the pump, and the discharge is where it exits. We're talking about incredibly heavy, rigid steel structures coming together here. And right here is where the human element can create an absolute disaster. In the real world, when a giant steel pipe is brought up to a pump flange, they almost never line up perfectly right away. There might be a slight gap or a tiny offset. Workers, who are usually under immense pressure to avoid project delays, will often use heavy equipment or just pure brute force to pull that pipe into place and bolt it tight. They figure, hey, just tighten the bolts, it'll close the gap. But pulling that heavy pipe introduces massive external strain on the pump casing. That metal casing flexes, and that flexing violently shifts the meticulously aligned internal pump shaft. Just like that, your first alignment is officially destroyed. Our second major culprit is something called the motor solo run. After the pipes are flushed, the electrical teams need to test the motor. They run it completely uncoupled from the pump to check for internal defects or excessive vibrations. If vibrations are detected, they have to adjust what's known as the soft foot. Think of it like a wobbly table at a restaurant. They essentially loosen and shim the bolts anchoring the motor to the base to ensure it's sitting perfectly flat. But wait, if you change the shims under the motor's feet, you're physically raising or lowering that motor. Once again, the motor shaft shifts and your first alignment is ruined. To fix this chaos, the final alignment checklist requires us to re-inspect three familiar points. Number 1, shaft alignment. Number 2, the DBSC, or distance between shaft end. And number 3, verifying that motor soft foot. But to ensure those first three actually stay perfect, we have to introduce a massive, absolutely critical fourth requirement. Which brings us to the ultimate gatekeeper of rotating equipment installation: pump and pipe parallelism. Parallelism dictates an unbreakable rule. You can never, ever forcefully pull pipes and pumps together. The flanges of the pipe and the flanges of the pump must sit perfectly parallel and perfectly spaced in a natural, resting state before a single bolt is tightened. And the stakes here? They're incredibly high. If you check the parallelism and find a minor misalignment, you might get lucky and fix it by slightly adjusting a nearby pipe support bracket. But what if it's a large misalignment? You can't just force it. You literally have to cut the pipe flange off and re-weld it in the correct position. And because you've just welded a pipe, you trigger a catastrophic delay of redoing all the hydrostatic testing and line flushing for that entire section. It's a massive setback. That's exactly why piping teams must be deeply coordinated with the equipment teams right from day one. So, to avoid those project-crippling delays, mechanical engineers use highly specialized tools to verify the gap between the flanges. We are not talking about just eyeballing it here. We are talking about microscopic allowable gap variations meticulously measured with precision instruments before the assembly is permitted to proceed. First up, we look at the overall gasket tolerance.
Let's say your standard plant gasket, which is the seal that goes between the flanges, is 4.5 millimeters thick. The resting gap between the pipe flange and the pump flange is only allowed a super strict tolerance of plus or minus 1.5 millimeters. That means the gap across the entire face must naturally fall exactly between 3 millimeters and 6 millimeters. If it's 7 millimeters, it fails. If it's 2 millimeters, it fails.
Additionally, we have to check if the flanges are truly parallel and not sitting at a weird angle. To do this, engineers insert a taper gauge at 4 distinct points: the top, bottom, left, and right of the flanges. They measure the gap at each point. The maximum difference between the largest gap and the smallest gap cannot exceed 0.25 millimeters. Just really think about that for a second. A quarter of a single millimeter is all the variance you are allowed on massive, incredibly heavy industrial piping. It's wild. Once these exact tolerances are cleared and the inspection reports are officially signed off, you can finally breathe a sigh of relief. You are finally permitted to insert the gasket and systematically bolt the piping and pump flanges together at both the suction and the discharge.
So the visual gap was perfect, the gasket is in, and the flange bolts are torqued tight. The machine looks fully assembled. Can we hand this rotating equipment over to the owner yet? Are we finally done? The answer is no, you aren't done. This brings us to the final iterative loop. You see, the very act of bolting those flanges together and compressing that gasket might have introduced a tiny new stress that subtly moved the pump shaft, so you must immediately recheck the pump-to-motor shaft alignment with your laser tools or dial gauges. And if that shaft alignment has failed its tolerance, yup, you guessed it. You have to unbolt the pipe flanges, figure out what pulled, realign everything, and repeat the entire process. This isn't just a simple checklist. It's practically an engineering philosophy. This meticulous cycle repeats over and over until both the pipe-to-pump parallelism and the motor-to-pump shaft alignment sit in perfect, undisturbed harmony. The machine must exist without a single ounce of external force acting upon its resting state. Only then can the coupling be installed to truly connect the motor and pump.
As we wrap up this explainer, I really want you to think about the massive scale of industrial construction. We've just seen the grueling effort it takes to properly align a single pump. It really leaves you wondering, in an industrial plant with thousands of rotating machines, miles of piping, and incredibly tight deadlines, what catastrophic chain reactions, from violent vibrations to blown seals and total plant shutdowns, could stem from just one engineer in a rush, forcing a single pipe to fit? Thank you so much for joining me. Keep questioning how things fit together, and I'll see you in the next explainer.